next segment of the Klingberg Wing Mark II development. I'm Raul Klingberg, your host. Today, I'm going to talk about wing joiners, one of my favorite topics, and I think it's critical to all of us. Anything that holds the two wings together, kind of a critical item. So, in a moment here, we'll get started, and we're going to go into some non-technical details, maybe a few technical points in there, about how to hold the two wings together. Come on along. Okay, the Klingberg Wing Mark II is a very demanding design for the wing joiner. The loads at 6 Gs are quite high. The spar caps carry about 30,000 pounds of load at 6 Gs. Those loads have to be joined together somehow in the middle. The whole thing has to be easy to take apart, easy to assemble, easy to transport, and not too heavy. These components have to be extremely efficient, very high strength to weight ratio. They have to carry not only the bending loads, but all the torsional loads also, plus the pilot is suspended off the aft end of the wing. So what I have here today are some mock-ups that I use for looking at various ways of joining the two wings together. This is just one example here. These would be two parts that come off of the main spar or joined into the main spar built into it. These would be carbon fiber composite, or they could even be titanium. And there'd be a center section of the wing here, just this wide. This is all full scale. And they would slide in like this. And then you put a couple of pins in here. Now, by the time you work out the design to get this center component built up to the proper thicknesses, this is all extremely heavy, 4 or 5 pounds. You have a couple of pounds per component here. It's just really not efficient. And part of the problem is that because the wing is so thin, my original wing was maybe 16, 18 inches thick, so that the wing joiners had a generous moment arm to work with in terms of carrying the bending loads. This wing is much thinner. I want the wing thin on this aircraft to maintain high speed capabilities. I'd like this aircraft to have a redline speed up around 100 miles an hour so that you could cruise between thermals at, say, 65, 70 miles an hour. And if I go to a thick wing where it's easier to carry the loads, you're not going to be flying that fast. So we have to find a way to efficiently carry these loads. When you design a component such as this, it's moving the load carrying from the outer surface where you'd get the best moment arm and actually moves it in an inch or so. And that means instead of having to carry 30,000 pounds of load out here, it has to carry 40,000 pounds of load here. It's a huge increase in load for just a very small change in distance away from the outer surface. So in order to be efficient, we want the load carrying members to be as close to the outer surface as possible. This design was interesting, but inefficient. So that has gone by the wayside. I looked at another answer over here that would look like this, that you'd have this curved centerpiece, you'd have a front plate and a back plate. This could be built by your average home builder out of carbon fiber composites, or it could even be sent off to a shop and be actually 3D printed out of titanium. That is possible these days. And there would be pins like this. This would be a similar lug sitting up here coming out of the wing, and to assemble the aircraft you would attach this to each side of the wing. This component would be built into the center rib that's going to carry the pilot out back. Once again, we're slightly below the surface here. There's a lot of loads here, 40,000 pounds on this pin at 6 Gs. A part that's somewhat complicated to make, doable by a home builder, but a little complicated, and unfortunately a little bit heavy. If this were all carbon fiber and carefully built and sized, it would still weigh over 2 pounds. And you got 2 of them, that's 4 pounds, and now you're just adding too much weight to the aircraft. Plus, anything that involves a lug or a spar sticking out of the wing, I have reservations about that, because as the aircraft gets transported around, the bumping loads, as this gets bumped into, banged into, somebody leans on it like this, it's going to be exposed to loads that far exceed what goes on it in flight, and especially in directions that it never sees in flight. In flight, it's not going to see any loads this way on this lug, but it could easily see those in transportation. So then you're having to design the wing joiner for transportation also, and that drives the design to a point where it's overbuilt for flight loads. So we have to be very creative here and design it just to carry the flight loads, yet not be susceptible to ground handling damage or transportation damage. Now, the Swift aircraft solves this problem in a fairly elegant manner in my mind. If you go on YouTube, you will find videos of Swift being assembled, and you'll see the two wing panels going onto a straight spar. The spar, off the spar, they hang the pilot's cage, and it's all very slick. But you have to carry this 7-8 foot long box spar with you, which is an entirely separate item. And not only that, the spar is straight and the wings are angled, and if you watch these assembly videos, everybody's being very careful on how they slide that wing onto the spar so that they don't get it in an angle and do damage to the aircraft. It's a little bit messy if you're not in a nice grassy field or a hangar, if you're out on a rocky cliff face at the edge of the cliff and you're trying to get your glider together and it's windy. You don't need to be handling an extra long spar and trying to work real careful to slide it together. Plus, transportation in the box, the fewer the parts, the better. So I want my wing attachment methodology to be integrated in with the D-tubes and the spar, so we don't have separate parts to carry around with us. It needs to be easy to align, needs to be near the outer surface to carry the loads best, and simple to build for the home builder, and at high strength to weight ratio. So I've gone through a bunch of different options. I'll run a little piece of other video for you here, and you can see what happens when you don't get it right. 3, there's 4 here, 4.
Well, that went.
I'm sure it was a little bit exciting, but it wasn't fun for me. A lot of work and 2 swipes at it, and I got a couple of broken wings. So I had to stop, back up, and rethink the entire solution on how to join the wings together. And where I've headed is something that is somewhat like I used on my original wing, yet modified for this particular aircraft. And if I can bring that up here, bring these parts up, get these guys out of the way, and get this sample out of the way, and bring up the other wing sample. Okay, here's another mock-up of the wing. I'm going to turn it around this way so you can see it. So what you see here is we have the D-tube, and this would be where the main spar lies, and then there would be this added section back here, triangular section, 1/2-inch thick sandwich panels, and it would actually form a box on the end. As you can see here, I don't have the bottom panel put in place, but you would have essentially a box that goes all the way around. Main spar, top sheet, a second spar, and then back again. So we'd have a nice square box, and this would be on each wing half, and they would butt together. Now, on my original wing, I had essentially a piano hinge set up, somewhat similar to what you see here. There were a series of lugs, which were counterspaced with lugs on the other side, and a bolt dropped in, and those lugs were here and here on the wing. Now that wing was thick enough. I had 4 lugs up here, 4 lugs down here, a 3/8 inch bolt, and it did the job. It carried the loads quite nicely. In fact, the wing joiner on my original wing was good for 36 Gs. So it was actually overbuilt, but it was within the acceptable weight range, so I kept the design. When the aircraft crashed, one of the few areas that was not broken was those wing joiners. So it really proved out to be a very efficient design, and I've created some samples here of what we'll be able to do with this wing and what we're going to test out on the next go round, and I have high confidence that this is going to work out well. So as we proceed here, I'm going to get into more details about how this is designed and built and how it'll integrate into the aircraft itself. Okay, so let's talk about these wing joining lugs. These are designed and actually built specific for each panel. It's quite easy to do. In fact, these aren't glued on. I'll pull the panel off so you can see them. You would build up these panels first. Now this happens to be a 1/4 inch thick panel, which is intended for the rear spar. These would be 1/2 inch thick, but you have a panel like this that you've made out of composites. You would put packing tape or some other releasable plastic covering on this, and you lay up, and I'm going to pull the other side off of here. Oh, I got an extra one here. You lay up the assembly right directly on the panel so you get an exact fit, and this is laid up as one long strip. The carbon fabric is wrapped around. You put on as many layers as you need to carry the load, and when it's removed, I then use a diamond wet saw to cut out the pieces. As you can see, there's a metal piece of tubing in here that acts as a bushing for the joining pin, and it prevents getting concentrated loads on the carbon fiber. There's one layer on the inside that bonds to the tube, and then the little divots filled on each side, and then layers are wrapped on the outside. I just used bidirectional 2x2 twill cloth to make these parts. This is for rear spar. This has an 1/8 inch thick layup on it. Now, these are joined together with a pin. Now, one can use a high carbon steel piano hinge. This is good to 320,000 psi in tensile strength, so the shear strength is 60% of that. This is small yet extremely strong. You only need a short piece of it to join those together. This has the same strength as a grade 8 aircraft bolt. Or I'm also going to look at carbon fiber pultruded rods. These are available in a variety of sizes. This is a 1/4 inch one. Here's a 1/2 inch one. These have the same tensile strength capability as the steel, yet these weigh the same as an aluminum part, so you would save a lot of weight. And as you can see here, they slide in and out fairly easy. I'm going to just pull this one out, and you can see those pieces fall off like that. So what we would have is a series of these lugs built on to these panels like this. The panel might actually be wider. Rather than 3 of these, there might be 4 of them, 5 if needed, and the lugs are also going to go down here this way, and the lugs will come across the bottom, and then we'll have lugs on the main spar all the way up. The length of these, the width of these are all determined by how much load they have to carry and where they're located. Now the advantage to this is, because these are located up here on this panel, they are as close as possible to the spar cap and are going to be most efficient at carrying the loads. Plus, we're distributing them out over a wide area. The total area of these lugs, when you add them all up, actually exceeds the area in this part that I showed you earlier. So they are actually stronger than this solution. And I like to think that they're probably a little bit more fail-safe. If you're going to over-design, suppose you have one bad lug or one fails, it's still going to hold together. I like to think of it as more of a fail-safe design. It's not one-point critical failure. That's the intention. I'll make the 1/2 inch thick ones on a piece of composite panel that I build up. And these are actually going to go off to a lab. I found a wonderful lab in Texas that tests composite materials. I'm going to send them the lugs. I'm going to send them some carbon fiber pins. I'm going to send them some steel pins, and they're going to do pull tests on these. And they're going to tell me both what the strength of these lugs are that I make, and we're also going to send a panel. In fact, I'm going to send these 2 panels with the 3 lugs on them, and they're going to pull the panels apart and find out how strong the entire joint is. So when you assemble the 2 wings, you're going to have the 2 halves coming together like this. You have to imagine the other half of the wing, and we're going to have lugs on the other side. They're going to come in. So to join the 2 wing halves together, you would start at the bottom, and you put the pin in this way through the lugs. Then you put in 2 vertical pins, and the bottom pin keeps the vertical pins from falling out the bottom, and then you put in the top pin, and that keeps the vertical pins from going out the top. And then all I have to do is provide a catch latch here to keep the horizontal pins from pulling out. So really we have a very efficient system for carrying the loads that are close to the spar caps, and then we're helping pick up the loads from the shear web here, and we're helping transfer some of the loads from the outer spar onto this strip. And this is straight this way as opposed to the 20-degree angle, so we don't have to worry about the oblique loading on these lugs. These lugs will be under oblique loading. They have to be made a little bit thicker to carry that sideways load, but back here they'll be in pure tension or compression, and they'll perform best that way. Overall, I think this is a nice solution. We don't have any parts sticking out significantly from the main structure of the aircraft, so they're not likely to get damaged in transportation. This entire box structure that will hold this lug and pin system will be actually hidden within the wing. There'll be an access panel up underneath where the pilot can reach up in and put in the assembly pins. There'll be a couple of small access panels up here. Once the pins are in, a little bit of tape over the top, and the bottom will be left open because it's going to be enclosed by a cockpit fairing, so we don't have to worry about any extra drag from that small hole in the bottom of the wing for reaching up to get to the pins. I'm going to look at, these have brass tubing in them. I'm going to make some more of this size with brass tubing. I also have some, I don't have it here. I have some 4130 chrome moly tubing, half-inch inside diameter, half-inch outside diameter, 7/16 inside diameter for mating with the lugs for these larger panels. All of that's going to go off to the lab to be tested. You and I can wait together with bated breath to find out how good they are when it comes back from the testing. So, here's a sample of the 4130 steel tubing that can be used for bushing. I was using it for a pin over here. Okay, so now this does actually generate an additional challenge. If the spar caps are here and the wing joining lugs are back here, you have to find a way to get the loads from the spar caps back into this box structure. Now, we don't want to carry it as tension, as a bond between this panel and the shear web, and we don't want to build one huge hulking big structure here because it would be too heavy. We have to efficiently get the loads from the outer wing. We need to carry them in and get them into this panel, and that's where the carbon fiber rods come in. I think I have a viable solution for this, and I hope I can show it to you here. And you'll now discover why we have the carbon fiber cloth that's joining these rods together at an angle like this. If you want to find out more about these carbon fiber rods and the spar cap methodology, go see the video on the spar cap tests. So what we're going to need to do is just flex these rods from the spar cap down onto the surface like this. We're going to have one like that. We're going to have another one, and another one. So we have an angle back here so that we can permit these rods to flex at a different point that will help them align properly with the angle we want them at. This is very difficult to do with one hand, as you can see, but here's the point. So you're here. Next one's a little further back. Get this guy out of the way. You got some guy in the middle. And I can imagine trying to glue this all together. There we go. That's a pretty good example. So you can see that the flex points are spread out here, so we have this bonded together at an angle here. Now, there will actually be 30 of these rods that go onto this upper surface. There will be small gaps between each rod. I plan on bending these, tack gluing them in place with some CA glue, and then when I do the final bond, I'm going to fill the spaces between the rods with the structural adhesive, and then I'm going to come over the top with 1 or 2 layers of carbon fiber cloth so that these rods will get spread out and bonded to this panel. And that way we're carrying the loads from a concentrated spar cap to a distributed spar cap and into this panel and into the lugs. It should be quite efficient and extremely strong. So I have high hopes that the next test of the spar will work out better than the video I showed you earlier. Cross your fingers, wish me luck. If this doesn't work, I'm going to have to re-engineer it again. It'll probably be another month or so before we find out how well that works, maybe longer. I hope you bear with me. Go see some of my other videos, look at the original aircraft flying, go look at some videos of the new model flying, have some fun, and I'm glad you're following along. If you're new, please subscribe and come along for all the fun we're going to have. Thanks. Bye.